Okay, so I have started out with this as my first slide for every talk I've given over the last 5 or so years. And the reason is because there is this framework that is our civilization, and it has these critical elements. Now you can argue about each one of them, which one's more important, but there are going to be 3 of them that show up in this talk. And they are going to be, of course, science and technology, and art is going to figure into it. And there's a moral tradition. Now, I'm not putting the moral tradition in here, but it's considered a mineral oddity, and those are fakes and frauds. And that's part of the moral tradition. And they wouldn't be fakes and frauds if there wasn't for that. So, moving right along with the buttons.
I can have it. Try that.
Okay, so do I need to point it here or up there?
I think it should be fine.
Okay.
I just had to like get it refreshed.
Okay. There are no mineral oddities. I've actually discovered in the last 3 weeks that that's wrong. But I'm going to save that for the end. And I guarantee you that you will be surprised, and I'm willing to bet that there will be probably only 1 person or 2 people in this room that will know what I'm talking about. So, MnDAT, of course, is always listing a whole bunch of different minerals. And the last time that I looked, it was more than 5,659 minerals. But in 2022, Hazen and Morrison worked with the 5,659 species, and they created a scheme of paragenetic modes and said that there were 57 modes in which minerals occur. There's quite a few modes where there's only 1 mineral that shows up, but there's a whole bunch of them for things like pyrite. I think pyrite's in 17 different paragenetic sequences. So paragenesis is just this concept in petrology, and it's an equilibrium sequence of the mineral phases. And the phases just means mineral species. And it's used in igneous and metamorphic rocks. It's used in hydrothermal deposits. It's used in vein metasomatism and is oftentimes associated with ore mineral deposits. And all it really means is there's this sequence that's going to happen. And it starts real early with the Big Bang. And these are the elements, and they've all been attributed to various parts of different things happening with different stars. Now, this is way out there in left field, and so we're going to move on without you actually having the chance to go through it, but everything is out there. So we're going to deal with environments and paragenetic sequences on Earth. So first question is, what is a solution? And are you aware that there are saturation levels of solutions? And there are immiscible solutions where you have one solution in another solution, but the two won't mix. And there are various types and properties of solutions: viscosity, density, temperature, things like this. And this was actually worked out by Paul Barton of the USGS in his studies at Creed. And it's one of the most useful diagrams that I have ever seen. And what he is basically saying is that as a solution, is involved in these things, the level of saturation for any one element or ion can be in the supersaturation range or in the undersaturation range, or it can be actually at equilibrium. But a solution a lot of times has more than one thing in it. And so it can be supersaturated for one thing and way down deficient in something else. And furthermore, they can change. So up here, at the top, gel precipitates are really kind of rare in the mineral world, but there are certainly some that show up. But in the supersaturated range, the fibrous crystals and very fine crystals are reasonably common, and skeletal crystals are reasonably common. Sector zoning is usually determined by color, and so sometimes it's pretty hard to actually tell the difference. John Rackavan spends hours looking at the sector zoning and appetites, and he does it using fluorescence because different zones show different fluorescences. And then when you get to equilibrium, you have got selective replacement of some crystals and also delicate growth banding and large crystals. And then you get down in the undersaturation and you can go from etching to complete removal. So we're going to stick with Colorado for all practical purposes because it's a great laboratory. This is the Pikes Peak batholith. And all of the things that are colored blue or dark purple are areas where there are plutons within the giant pluton. And these are the places that you go to collect this stuff. And you can see in various places.
Reacting or something you had up there.
Oh, okay. Okay. I hope it was a good something.
It was.
So you can. Yeah. Oh, yeah. We pointed out before. It's right there in your backyard. Okay. So anyway, this is the result of solutions. Now, a magma is a solution. And where there is a transition to magma to some sort of hydrothermal fluid and all that's beyond the scope of this discussion. And where there's the transition from supercritical water to ordinary water is beyond this discussion. But the point is that these are, in fact, solutions. And everybody know what this is? Graphic granite. Anybody else want to venture a guess on what it actually is? This stuff is quartz, but it's skeletal crystals. And the reason that it's like that is it simply grew fast enough that it didn't have time to fill everything in. Now, that's not the only place you find it. It's just that this happens to be the best example of graphic granite that I've ever seen. Paul Barton came to visit the museum, and I had this thing sitting out on the counter, and he goes, I've forgotten what his wife's name, but I'll say Sharon. Sharon, look at that. That's the way the 10 Commandments looked. And now, who am I to argue with Paul knowing what the 10 Commandments actually looked like? But anyway, the point is that those crystals couldn't fill in. They were growing too fast. So that's the same thing. This is amethyst, but it's a skeletal crystal. And it was growing fast enough that not everything filled in. Now, it's euhedral with respect to smooth faces and that, but these are all indentations and everything's in the correct crystallographic stacking pattern, but it's rapid growth because it's a supersaturated solution that was producing it. This is sector zoning from right here in Colorado. And in this particular case, it didn't get filled in with more fluoride. It's just these corners that started growing, but that's, again, on that chart. And that's a giant crystal. So this is at real close to being equilibrium. And not everything that's a giant crystal is this size. I mean, to me, a giant crystal, a lot of times is only something that's like this, but giant crystals can be giant crystals. And then when you get out in the range of undersaturation, this doesn't happen to be from the Pikes Peak batholith, but it's a better example than I have from any place else. And it's from Crete, and the amethyst actually grew on top of minerals that have been completely resorbed and they've gone away. And so that's on the underside, the bottom side of that graph where you get removal. So these solutions can change their composition through time based on the source and the availability of the contributing materials. Things like faulting can interfere with it. It can be something that's happening over geologic time. It can be something that really happens pretty fast. And in a lot of cases, crystals aren't really growing that slowly. They're actually growing pretty fast. And this is from Kavnik, Romania. We just got it the other day. And the reason that we got it is because this quartz is showing an overgrowth of dolomite, but the dolomite is in what's called snow on a fence post texture. And what is that showing you is that there was a flow of mineralizing solutions, hydrothermal solutions, if you want to call them that, coming from this direction. And the flow was pretty good. It was moving quite well. And so there wasn't any attachment on the, not the upwind side, but on the upflow side. But this is the lee side. And so there's not any flow of hydrothermal fluid that's interrupting that material settling on it. And if you stop and think about it, this is SiO2, and this is calcium magnesium carbonate. Those are remarkably different fluid compositions. And so you had a radical change in between the deposition of those two things, in spite of the fact that they're directly connected. And this will soon be on exhibit. I haven't quite gotten it out yet, but it will be. So let's look at the Colorado mineral belt, which is actually divided into three parts. Up here to the north is the northern section of the mineral belt. And basically, most of the deposits are related to an intrusion in the subsurface, not something that's truly volcanic, but deeper. And it's something that is much younger than the Precambrian host rocks, which are granitic and metamorphic, and are basically the same, running at depth pretty much all the way down through it. And then in the middle section, most of the ore deposits are found associated with limestone. They're in carbonates. And then down here at the bottom, everything is tied up with the San Juan volcanic field. And so we've got three different laboratories, and we can look at some of the different things that have happened according to various paragenetic schemes. So we'll start in the north, and we'll look at tellurides. Tellurides are distinguished by being rare. And they're often valuable because they contain gold and silver. And they're rare. And a lot of times they're unrecognized by the untrained eye, but they're rare. And it's difficult to find specimens to study, and that's because they're rare. And they're hard to identify because you don't get to see them very much, and that's because they're rare. So, when I say rare, we're talking about on a worldwide scale that they're rare. Colorado, Kirkland Lake, Nagyog, Kalgoorlie, and Fiji. And there's some things over in here that I don't really know very much about. There are Russian deposits and Chinese deposits, but comparatively, they're still rare. And this is from the original location for the discovery of tellurium, and it's the mineral sylvanite, and it's what they call tellurium. And it's got this sort of pattern, and what it amounts to is twinning in the sphalerite. And the reason it's called graphic tellurium is because the people that have a good imagination, this is the Rosetta Stone in the British Museum. People look at it and they say, oh, that looks just like graphic tellurium. In fact, actually it goes the other way around. The reason that we're going to call it graphic tellurium is because it looks like that. And this is the piece that this comes from. So rarity does not equal an oddity. I had this discussion with Marty Zinn. He was talking about his crystallized rose quartz. And I said, Marty, it is rare, but that doesn't mean it's odd. It only means that it's rare. And he agreed eventually. Okay, this is from Boulder County. It's from the Cache Mine in Boulder County, and that is gold, and that's petsite. And yes, the tellurium mineralization is rare. But the other part of it is people look at something like that and they say, well, that's really rare. That looks like some sort of a lizard or maybe a squirrel or something like that. And as it turns out, seeing animal and human forms in inanimate objects is a characteristic of us. You know, all you got to do is be around your 4-year-old and he looks at something and says, that looks like a washing machine. And you're going, oh, wait a second, that's a lawnmower. Well, that doesn't look like a washing machine, but I can't crawl into his mind. And so it can be because of an idle mind, but it can also be the result of an obsession or maybe keen insight or artistic genius. And there are plenty of people then in the Impressionist period that made a lot of money off of that artistic genius stuff and seeing things that the rest of us might not have seen until they put it on the canvas. Okay, so let's move to the south into the central mineral belt. And we'll start in here at Gilman and Leadville and Aspen. And these are all deposits that are in limestone. And it's got a lot of geologic history that goes in there. If you look at the geologic timetable, what we're really talking about is the formation of the Leadville limestone, which is Mississippian in age. And this is representing sea level and how far it goes away from this present line. This is present day sea level. And so you can see from the Precambrian up at least until right here, everything is in a period where sea level was a lot higher. And some of this probably has a whole lot to do with spreading in the ocean and whether the plate had time to sag or not. And if it didn't have time to sag, then the ocean wasn't as deep. It's fairly complicated. The amount of water that was available is pretty much the same. And this wavy line means that there's an unconformity there. And so at this point in time, sea level went backwards the other way. And exactly how far, we don't know. But the point is on this, that this is where the Leadville limestone is crystallizing. And furthermore, there also are Devonian and Silurian and Ordovician limestones that underlie the Leadville limestone. And up here at the top, sea level has dropped down almost to the present level. And then there's an unconformity. So more and more of the ocean went away. And this has a lot to do with the kind of stuff that was actually happening with the rocks. If you look at the modern world, there are carbonate reefs in the areas that are colored green. And it's basically shallow water deposition. And in areas like this on continental land masses, there's evaporites that form. And it's those reef situations and large accumulations of carbonate material, mostly calcite, that is responsible for being the host rock for everything in Leadville and Aspen and Gilman. But it comes with a twist. It's all in the warm water, and that's because CO2 can combine with carbonate in warm waters. So this is the late Paleozoic, Carboniferous, just a little bit later. And this is, and that's the equator. So we are in an environment that can produce carbonate rocks. And if you look just at a map of the US and Canada, the point is that this is primarily limestone deposition all the way up in Ohio, as Terry will point out, and all the way down here, and certainly in Colorado. And the amount of limestone that was deposited is a lot. And the models that we use today don't really work very well when you go back to this time. There's some things that are sort of strange. You can talk with Rick Sarg about it, and he says, well, you know, we think we would see this, but that's not what we see. And what we seem to be seeing is something on this open shelf that's up here, and as the water is receding or advancing, that seems to affect the kind of rock that we get. And these are just eroded carbonate sands from whatever was being deposited up here. So the Leadville limestone is actually a dolomite. And there's 5 or 6 different models for how it forms. But the key one is, and this is the point, is that to get regional dolomites, and this is what Rick Sarg was saying about when it's not like what we see, these are regional dolomites, you have to move sea level. And when you move the sea level, you can get an influx then of magnesium-rich brines which move through it. Now, whatever the model is, that's the thing where there's the difference. But the point is, there at the end of the Mississippian period, we have got an unconformity. And so they're moving that sea level, that shoreline. And in the process, we get the dolomites. So when you do that, as it turns out, there is a smaller unit cell in dolomite than in calcite, because magnesium ion is smaller than the calcium ion. But that opens up space in the rock, and that becomes very important. So we've got this laboratory that we're going to put all of this stuff in, and furthermore, when that sea level drops, this is the uplift of the ancestral Rockies. So we're moving it up. And that's going to make it available to fresh water, maybe to more rain, but certainly more water that can move through it. And what does it do? It dissolves and reacts with that limestone. And in the dolomitization process, which is probably coinciding to a certain extent, preceding to a certain extent, we are getting something that is a great receptor for mineralizing fluids. And this is just a diagram that Ogden Guido did. Devoto modified it in 1982, but the point is that up here above the Leadville Formation, when you uplift the Rockies, you're eroding the limestone. And that is creating cave systems. And there's a hell of a lot of difference between putting little bits of ions in little bits of open spaces, the whole thing with mineralizing mineral-rich solutions. So this is the ancestral Saguache uplift. That's Leadville. That's Gilman. That's Aspen. Most people don't know about the Gunnison paleokarst. Karst just means cave systems. And so those ore deposits are all in these karst systems, which means caves. And if you look at the process of how you get a cave, you start out with a water-filled tube. They call it a phreatic tube, and it's filled with water, and it's dissolving it. And over time, you actually get to the point where the tube's big enough, there's not enough water to fill it, and can actually partially or rather completely drain. And when it does, the can cause things to collapse. So you got all this rubble down here. But then you can fill up all of that rubble with whatever those hydrothermal solutions might bring in. And that is basically what happened at all three of those districts. So there's some sort of unique things that are going on. And I don't want to spend a whole lot of time on this, but the point is there are 1, 2, 3, 4, 5, 6 steps to this mineralization process. And there are different minerals that formed in each one, and each one of them is part of a paragenetic sequence that is an orderly physical and chemical process. And this is all the minerals that were found at Aspen. And you can tell it's Aspen because you got piercite. You don't find that in any of the other districts to amount to anything. So these are different stages in the process, and this is a paragenetic chart. If you look at a map of Gilman, each one of these areas, they call them a manto, that's a mining term, is actually a cave system. So you were filling that up. Now, we don't think of caves this way, but I'd rather have a cave full of even lead zinc ore, and if you throw in some silver, that's even better, and if you throw in some gold, that's even better. But I'd rather have one of those than just calcite crystals. If you look at a cross section at Aspen, this is a cave section that goes from Aspen Mountain, where all the skiing is, all the way over to Smuggler Mountain, ore deposits essentially all the way. If you look at Leadville, this is a map showing the shape of the ore deposits, especially here. It looks like a cave system. Now, back in this area, we've got a whole different process going on, and there's deep intrusives that are feeding material, but that cave system is there. And we know that we're dealing with limestones. This is a very famous specimen of silver from Aspen with half of a gastropod preserved in it. And we know that some of those solutions were supersaturated because this is native silver crystallized from Aspen, and that is definitely a dendritic type growth. It's growing very rapidly, and it didn't have time to make one big crystal. Instead, it branched out and made all of these small ones. One other thing that we see in this general area, does anybody recognize where this is? Yeah, that's the Sweet Home down here, and the Detroit cities up there. All of this, and that means there's oxidation going on, and this is post-mineralization oxidation. It's up the oxidation process. creates new minerals. And so you have a whole nother paragenetic scheme that is going on there. And this is straight out of Ransom's work from, I don't know, 1905, 1910, something like that. And he cut a vein in half and he said, okay, up here, we've got the oxidized zone. Down here, we have the water table. And there can actually be movement of water in here according to groundwater levels. But generally, there is an area where that water table has been concentrated. So up here, we've pretty well stripped out a lot of material, but there is what we call gossan that's in the outcrop. And we've leached a whole lot of those metallic elements, and they're gone. But then down here, what's happened is those metallic minerals have been oxidized, and so you're getting, among other things, maybe pseudomorphs. No, okay. So maybe I pushed the wrong button. Yeah. It's not that I have fat thumbs, folks. Okay, so down here, below the water table, we have an enriched zone. And this is where you find things like perargyrite and proustite. And down here, you would find tetrahedrite and galena that has a high silver content. But there are various minerals that are found in each one of these zones. And if you look at the overall deposit, it pretty much turns out to be just like clockwork. The hard part is the geology of figuring out what the present day surface has to do with the surface that was back there in geologic time. There.
Okay.
Okay. So this is a specimen that actually shows the water table. And these are sulfides. It's mostly galena. And these are mostly siderite. And that's the water table. And this has all been altered from this. So at Leadville, this becomes very, very, very important. And the primary minerals are galena with silver as an impurity, and argentite, silver sulfide, and tetrahedrite, which is a argentiferous variety that will have silver in there, but it's copper, some iron, and antimony. And those get oxidized, again, as a part of a paragenetic sequence. And you end up with cerussite up here coming out of the galena. You can also get anglesite. And down here, the argentite in this near surface oxidized material is chlorargyrite. And if you throw in some bromine, and there's some in there, you get imbolite. And down here with the tetrahedrite, you're getting native silver right there at that enriched zone, along with some argenojarosite, which I think is, let's see, it's not Rakuthan's favorite mineral. It's Virgil's favorite mineral, I think. So actually, it's jarosite, and I've always asked him why he didn't like argenojarosite, and he said, well, jarosite's everywhere. You can work with it. This is something that's more rare. Anyway. So the point is, and a whole nother kind of paragenetic sequence. And this is a cube of galena completely covered over with cerussite. It's from Leadville. This is minium replacing galena, lead oxide. Euhedral crystal, great pseudomorph. This is chlorargyrite. And the thing that is really noticeable is that it's in these streaky, drawn out blobs. And this was the thing that made Samuel Franklin Emmons famous, was that he figured out that this texture was showing that the solutions came from above. And it's part of an oxidation sequence. This isn't something that came up from below. This is something that came from above where you were oxidizing material. The silver was combining with the chlorine and with bromine if it was available. And you have this dripping form. And if you read his monograph, it's the first truly great monograph that was ever turned out by the USGS. And it reads like a novel. It's a wonderful, wonderful book. And, you know, suddenly he says, this stuff was formed from solutions that came from above. And that's the texture you're seeing. It's, again, part of a paragenetic sequence. And this is prime zinc ore. Doesn't look like much. I mean, these are iron oxides, and it's got all these open spaces where something was completely removed, probably sphalerite. And the white crystals are hemimorphite. And because the hemimorphite is a zinc silicate, that's prime ore, different oxidation paragenetic sequence. Down to the San Juans, we have got a series of overlapping calderas, giant, giant things that are eruptive sequences on a scale like, what was the one that went off in the Pacific? Yeah, Krakatoa. Anyway, same kind of thing. And there's a center of these in the area around present-day Crete. And there actually are several calderas that all overlap right there at Crete. And because the collapse amounts to faulting, you're emptying a magma chamber below, and so there isn't anything to support it, so everything breaks and falls down. And that leads to faulting and openings. And so brain and surface drainage can enter those cracks and work their way down, and they have created an ore zone below. And the heat that is driving all this circulation of water is from the subvolcanic stock that fed the volcanoes to start with. So this is a cross-sectional diagram showing the two major fault systems that were actually mined successfully: the Bulldog Mountain Fault Zone, which is more recent mining, and the old Amethyst Fault Zone. And the Solomon Holy Moses is not really something that economically was very important. But the survey discovered through the years that if you were connected at least at depth with that Amethyst Fault Zone, the chances of having economic ore deposits were very good, and that's what led to the discovery of the Bulldog Mountain system. So, again, a paragenetic sequence, all worked out by looking at the rock, looking at the field around you, slicing off pieces of the rock, looking at the polished sections, slicing off pieces of the rock, grinding them down so they're so thin it'll pass light, looking at it with a petrographic microscope, and you can work out all of this kind of stuff. The idea is not for me to go through it, it's simply to point this out. This is the Amethyst fault system, and it has hydrothermal fluids. Hydrothermal simply means hot water with whatever's in solution, and it is boiling down here, and that creates steam which goes up here and it condenses on the wall, and then it drips down and actually forms some stalactites. And there's a dam up here, and there's a breccia dam. It's a breccia dam, and that has dripping water, and that forms stalactites. And some of these things get to be sheet-like features. And then time passes, and with the passage of the time, these are little stalactites. Now, this isn't, and this isn't out here, but here's the episode where the vein was open and water was dripping, and it's a very well-preserved paragenetic sequence. And then it fills up, and you begin to get crystallization on top of all of that stuff that was going on before. And in fact, we can go back, and you can now see that we have more crystallization out here, some of it this finely banded agate, amethystine agate, and then much more pure amethyst. So you have a supersaturated solution. That's silver in chalcedony is what it amounts to. It's a pocket in the amethyst, but the point is those are basically skeletal crystals. This is a skeletal crystal. I didn't mean that. The silver was skeletal. It's dendritic. This is a skeletal crystal of galena. It's grown so fast that it hasn't had a chance to fill in from supersaturated solutions. Okay. We're going to completely change gears now. If you have studied crystallography and you're old like me, there are 6 crystal systems. If you took a modern course, especially if you had a European professor, there's 7 crystal systems. And what they're haggling over is the difference between hexagonal, trigonal, and hexagonal, hexagonal. But the point is that they are actually defined by a fold of rotation. And what a fold is a form of symmetry where this is exactly a mirror image of that. And so there's a line in between my 2 little fingers, and that is that dividing plane that says 1, 2-fold, identical on both sides throughout the entire depth of the crystal. And if you will notice here, we have a 1-fold rotation. And sometimes you have to invert it in the triclinic system. It's the lowest symmetry. Monoclinic has got 2-fold, orthorhombic, 2-fold, and different kinds of planes. Tetragonal, 4-fold, hexagonal, trigonal, 3-fold axis, hexagonal, hexagonal, 1 6-fold axis, and down here 4 3-fold axes and 3 2-fold axes, or 4-fold according to how you orient the thing. Okay, that's the basic crystal system for all of our minerals. Now we have some cryptocrystalline kind of things, so you can get in discussions about opal and things like that. But the point is, we define minerals with those systems. Engineering and science have created quasi-crystals. And quasi-crystals are ordered, but they're not periodic. So, in a mineral, you have a unit cell, and you stack it right on top of the other one, and you stack it again, and you stack it again, and they're all the same, and so the symmetry stays the same. A quasi-crystal, you can't do that with. But it does have a fold orientation and symmetry. And like it says, the first ones were all synthetic. And then they found this meteorite in Russia. I don't know how to pronounce that. I'm going to call it Toktarika meteorite. And in the Toktarika meteorite, when they did the research on the thing, they found what they are calling It's either icosahedrite or icosahedrite, and I don't know exactly which one's right. And look at that formula, Al63Cu24Fe13. Now, if that's not a mouthful, I don't know what is. That is one hell of a formula. And they found decagonite, which is Al71. This one's got nickel in it, 5. And there was, within the last 8 months, there was a book that came out, The Mineralogy of Meteorites, and I was reading through it, and there's 4 pages, that's all there is. And it's a single chapter in there, and the guy is talking about the aluminum, copper, nickel minerals, and there's this whole discussion about, well, if this exists, then it has to exist, but if it doesn't exist, then it still exists. And the language, I wish I'd brought it with me, but I didn't. I forgot it. It's sitting at home on my dresser. But you know, you read through it and you go, you guys are talking around in circles. There's also another quasi-crystal that has been found in a fulgurite from the sand dunes down at Tucson, and they did the work there at U of A. So the powers that be in science have now created a new mineral system, crystal system. And it's the icosahedral system, and it's named for the icosahedrite. And it has a twofold axis and a threefold, I mean, not axis, twofold, threefold, and fivefold. That's not in that other stuff. But it has a diffraction pattern. You can aim a beam of X-rays into it and it will show you where the ions are. This is the twofold scan, and that shows you that's the twofold plane. It's got a threefold pattern. And this is it, 1, 2, 3. The other parts are just the other part of the thing. And in each one of those, you can fold it up and it's the same. And there's a fivefold, completely forbidden by our crystal symmetry that we deal with in mineralogy. That's 1, 2, 3, 4, 5. Okay, so now we have several minerals that don't fit in the standard definition for a crystal. And one doesn't even have a name, but they have been deemed to be minerals. They are in MnDAT. And that is an oddity. Thank you very much.
All right. Do we have any questions for Ed?
Don't ask me if we have a specimen of icosahedrite in the museum. The answer is no.
Aw. Anybody? Anybody?
You know what the synthetic
Oh, there's a bunch of them. They use them in electrical, ceramic type things all the time. I don't know a whole lot about it. I didn't even know there were quasi-crystals. You know, I actually wrote down on a piece of paper, if it were me, I would call them different states. Most of the time that's reserved for a vapor phase, a solid phase, or a liquid phase, but maybe this is a fourth state of matter. I don't know. But without so much as a how do you do, suddenly, and you can look it up in MnDAT, that crystal system is in there. And one of the guys that worked on it is at Princeton. He's a brilliant solid state physicist. But how on earth anybody got convinced into sticking it into the mineral world, I'm not real sure about that. And that is an oddity.
Indeed.
Thank you.
Yeah.
Huh? Well, the
Those three.
icosahedrite and the dodecahedrite do, yes. But it's natural in outer space. They say that the way that was formed was from collisions in the pre-solar stuff, where we're getting chondrules and things like that in meteorites, and that the collisions probably help create this. I'm not real sure how the collisions create order, but it is a limited order. So should the magazine change its name, Terry, to minerals and quasi crystals or something like? I mean, you know, that's really quite disruptive to the whole science. I don't know what to think of it, but it is odd.
Definitely odd. Cool.
No,
All right. Oh, yeah. Well, thank you again to all of our speakers today. Hope you all enjoyed day one